Hello, students. It's me. I'm still trying to get the camera high enough so you can see the whiteboard, and I will not be just, yeah, that you can see me too. So let's try this. No, that's not. That might do it. Okay, if I squeeze down a little bit, you can see me on the whiteboard. Let's put that over there a bit more. So good morning. Great. Okay. So I got Louisa, Ellie, Isabella. Super. Nice to have you. And I got a couple more joining in. That's terrific. There's Alicia. Thanks for joining me, all of you. And I've got both books. So, hello, Lola. Thanks for joining us. Right. So our goals today, Chelsea's here. Good. Our goals today are two. One is I want to make sure you know how to write up the lab and you're comfortable with that. We'll have it due when we return to school. I don't need you to send it to me. I really can't grade that easily. And then we'll take your questions first from chapter 8 in book 1. And then if you have anything in book 1, although I don't think we haven't gone through all of that yet. So once we run out of questions, we'll take some time in our time remaining and talk about book 1 and some ideas that will prepare you then to do problems and the reading and stuff once you get there. Okay, shall we begin? So here we go. Go ahead and get out your labs, and I will get some markers ready. So we're talking about the spectroscope labs. And essentially, you know the parts that probably should be there. I think we had an objective. And we're trying to find the concentration of Powerade, right? The concentration of, what did I say? Brilliant blue dye in Powerade. So we had an objective. We had the materials because we had a couple new things. We had cuvettes and we had, whatever else there. The spectrophotometer as well. Okay, this is not a spectroscope lab. Sorry, this is a spectrophotometer. Okay, pardon me. So spectrophotometer or spectrophotometry labs, however you want to title it. Okay, then for data, I saw everybody's got their data. And I'm sorry, our machine didn't work that well. Some years it just does not. So use the data I gave you, and you should have then some kind of graph. So let's remind ourselves of that. Absorbance is on the Y. Absorbance has no label. It's just a decimal representing, the greater the number, the greater the absorbance of light. And over here was concentration in moles per liter. So when I hello, good morning, Amina. Thanks for joining us. When I last left all of you, a lot of you are just realizing that you did your graph wrong. And I don't know who my last person is unless you have a different name than your email. So the graph that we did, we had to have out as our maximum here, the pure stuff, the concentration of the pure stuff. So that number out there has got to be small. It's got to be, what was it? 2.0 times 10 to the negative fifth, right? So that's got to be this. So you're going to have to divide up your graph carefully to plot all your points. Now, I realize, and Sophie, great. And Antonine is here as well. Thank you for joining us. And I have also, gotcha. All right. Thank you both. Good. So you got a series of points. You're going to draw a best fit line through the points. Eventually, you'll do this with a calculator in college and so on, okay? So get your ruler, draw through the middle of your points. It should go through 0, 0. I hope it does. And then we come to the power aid. Okay, now, if you remember, we had to take the power aid and dilute it by 2. That's the data I gave you. So 50% of the power aid was on the graph. Yeah, 100% was way out here. It was off the graph. Now, I could extend my line. That's called extrapolating my data, but it's less accurate. So if I tried to find it out here, in the middle of nowhere out here, it wouldn't be as accurate. So instead, we cut the power aid in half on the day that we did this last year or 2 years ago. And we got a value for 50% of the power aid. So let's say that value is here, whatever it is, okay? So what I'd do is I'd say, okay, that's my absorbance. And let's say that's 50% of power aid brilliant blue dye. I'm going to abbreviate that. Okay, then you got to come down. Boop, 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 boop. You know how to do this, right? And find the concentration in moles per liter. Now, that's the concentration of what? Not the pure Powerade, but 50%. What are you going to have to do with that value, folks, when you get that? If I want the concentration of the value, somebody type in a little answer. What will I have to do to get the value? So that's 50% of the power multiplied by 2. Lola, yeah, not by 12. I think you meant by 2. Yeah, exactly. So Lola's right. We're going to have to double the concentration that you solved for right there. Okay, good. A lot of you have that as well. Dynamite. I'm glad you're with me. So I'm just reading other comments. So the points should not be plotted along the same XY axis. Bella, I'm not sure I understand your question. So you may want to rephrase it. And looks like Lola, that's right. Exactly right. And your conclusion is going to be really short, right? So conclusion, the concentration of Powerade was bottom, okay, moles per liter, whatever it happens to be. Yes, I know it's a small number. They don't put a lot of dye in that stuff, and yet it's an intense color, isn't it? Kind of wild. Do you have questions about the lab? And again, for those that joined us later, the lab will be due in January, whenever I see you again, okay? So just hold on to it till then. Questions about how to write up the lab? So Bella writes that the points, should they be along an order? No, you're going to put the points first, wherever they plot, Bella, okay? And probably, I hope everybody, you get a line that goes through 0, 0, because if it has 0 absorbance, probably it's got 0 concentration. So you'd put a line first, then use the line. But the line, Bella, should be based on your points. So do your separate points first. Exactly. And then so the concentration is whatever meets at that same spot. If you mean the absorbance for the 50% power, yep, boom, we hit that. And then we come down and see what that is. And then we got to double it, of course, to get the percentage of pure Powerade. Good. Any other questions, comments about the lab? Want to make sure you can do it on your own and finish it up at home? Yeah, the conclusion, Alicia, is just what? Answer our objective. So what did you find for the concentration of the Powerade? Just put it in a little short sentences. Usually conclusions for me are really short. I'm not going to have us do a source of errors on this one. I'd rather maybe talk about that when we're back together. So no source of error. Exactly. Exactly. Good. Are we okay? If we are, let me know and I'll erase the board. Yeah, you can put the graph under data analysis. That's probably fine. Anyway, that's Beer's law, and Beer's law has to do with one way to measure concentration of stuff. In chapter 1, it's going to be used the idea that, hey, I can also measure not on this machine that we use, but on a machine where a reaction is happening as it goes on and the color changes. I can measure the speed of that reaction based on the change of the colored species or chemical that's formed. Okay, so let's erase. And then I'm going to take, I think, questions first on chapter 8. So we'll see what questions you have on chapter 8. What I will do also is I'll send this to everybody under the Google chat or whatever. Okay, so if you missed something, you want to go back and look at the video, you'll have it as well as folks that couldn't make it this morning. Okay. Great, I got one already. So, Alicia, you're on page 488, number 10. Let's everybody turn to that, and we'll have a look at it together. Maybe you guys can give me some help this morning, too. Okay, here we go. Oh, it's a long one. Let's see what we got. Okay, the penny. The penny. This is kind of a cool story, actually. And Feeney's here. Good morning, Feeney. Thank you for checking in. The penny was removed from circulation in Canada in 2014. Cheryl's Canadian, by the way. Okay. The United States may soon do the same. I don't know. The major reason for this move was the rising value of the copper metal. When the copper's value increased, pennies were produced as a zinc slug with a thin layer of copper. Zinc is cheaper than copper, so pennies are mainly made out of zinc with a thin coating of copper. Zinc reacts readily with hydrochloric acid, while copper does not. A triangular, we could actually try this. I got a couple pennies upstairs. Good. I mean, in the lab, I don't have chemicals, acids here at home. Okay, anyway, you file off a little corner of it, corner of the penny, to expose the zinc slug below it. The zinc reacts with the hydrochloric acid, releasing bubbles from the nicked area. What are the bubbles? Do we know? When a non-precious metal like zinc is put in acid, what bubbles, what gas forms? You write an answer while I'm continuing here. Releasing bubbles from the nickel area until nothing remains but a thin shell of copper. Whew. Okay, if 0.948 liters of, it's in the problem, isn't it? Hydrogen gas. Okay, hydrogen gas is collected over water at 20 and a pressure of 752 millimeters of mercury. Determine the percent by mass of copper in the tube. This is really a fun problem, so this is a good one. Exactly. Good. A lot of you had it anyway. Yeah, H2 gas is right. Okay, you ready? Here we go. So imagine here's the penny, and inside is the zinc, and it's mostly zinc. Okay, and the other stuff on the outside is copper. This is really kind of a fun one, so let's enjoy it. Here we go. So we've got well, let's write a reaction, can we? Okay, you can help me with that. So I got zinc, solid, plus, what is it, HCl? Probably. Yeah, HCl forms H2. And now you're going to help me balance that sucker. Okay, so already you got something you need to balance. What's the problem here? And we'll figure out what else forms, but really this is the important thing. Wow, Bella's on the fly. Woo, good. Okay, Bella, so I agree. She's got a 2 in front of HCl. That's right, because she got 2 H's here and she's going to make a salt that's floating in the water, ZnCl2, which we don't really care about. But what that means for you and I is I got a 1-to-2 ratio. Or sorry, no, I got a 1-to-1 ratio, 1-to-2 with the acid in case we need that. Okay, but I digress. Let's see what we got. So the hydrogen gas, we got 0.948 liters. And it's collected over water. Okay, so H2 collected over water, H2O, at 20 degrees C. And as you could probably guess, we need a piece of data. Okay, so the total pressure is 752 millimeters. Whoops, I could write this morning. 752 millimeters of mercury. Good. Okay, we want the percent mass of the copper in the 2 point. Okay, so ultimately percent mass of Cu in the 2.586 gram penny. Okay, well, folks, this sounds complicated. That's supposed to be a percent symbol. This sounds complicated, but it's not. Yeah, exactly. Good. So Bella's on the right track. She's going to get the moles of H2. Okay? And ultimately, you're going to get it with Pivnert. But here's your problem. Exactly. So Antonine's probably on. The total pressure is this. We need the pressure of H2. So the pressure of H2, wait a minute. Why do I have a T there? It looks like temperature because I screwed up. I think Anthony was telling me that. Thank you, Anthony. So P total. Sorry. I want the pressure of H2. Sorry about that, folks. So I got to take what? I got to take the P total minus the pressure of what that it was collected over. Who remembers we did this maybe last week or so in class? Minus the what? The pressure of? Anne-Sophie. Thank you, Anne-Sophie. I lose track of these extra names. What do I got to subtract out here, folks? The pressure of what? Shall I give you a hint? Yeah, the pressure of what? What do I got to subtract? The pressure of the, and while you're hopefully getting the right answer for me, I'm going to go back and find that piece of data. Some of you can also help me find that piece of data. It's in a table. It's on page 479. And it's in kilopascals. How unfortunate. That's just stupid. Golly. Okay, so here we go. We figured out. No, we didn't figure out. What do I got? Guys, it's H2 gas, but it's collected over water. So think of like this whole thing happening in a watery solution. So I got to subtract out the vapor of the water. Exactly. Okay, so minus. This is called a wet gas problem. We talked about this the other day. So because there's some water vapor that gets up into where the H2 is collected, I got to subtract that out. So here we go. So it's 752 millimeters of mercury minus, okay, you ready? The table's on page 479. and minus at 20 degrees. Is it at 20 degrees? Yes, it's at 20 degrees. So I got minus 2.34 kilopascals. 2.34 kilopascals. All right, where am I getting that? Right there. That's where you find your water vapor pressure. Okay, now I got to multiply that first by something to convert it. And I do not remember this, so maybe you can check your notes for me. How do I convert kilopascals to millimeters of mercury, or torr as it's also called? I'll look in the book, but maybe you can find it quicker than I. I flipping don't really remember off the top of my head. It's like 101 or something. I don't know. Back here somewhere. I don't use kilopascals all that much. Somebody find it. Kilopascals to millimeters of mercury. Thank you. Good. Bella's on the stick. Here we go. So it's 101.3 kilopascals to 760 millimeters of mercury. Alyssa has it as well. So we're going to multiply that. So times on, I'm sorry, my board's looking so small here, times that ratio. We want to get rid of kilopascals. So I'm going to put that about on the bottom, 101.3 pascals. And on top, 1 atmosphere, or 760 millimeters of mercury. Sorry to have to squeeze that in. So you got to do that first, gang, don't you? So multiply these suckers, then subtract what you get from 752. So, or you can just put in a lot of parentheses on your calculators. All right. Okay, so my people, let's see where we're going. We need the pressure of this, because eventually we got to get Pivner, we got to get the moles of it, and then change it to grams, and then life will be good. We can finally answer their question. Okay, so let me make a little board space. You guys need to find out this pressure for me in millimeters of mercury. Can you do that? And a couple of you type it in and compare. And while you're doing that, I'm going to race over here a bit so I have a little room to write. Okay, so okay, somebody got the pressure for us. I know there's a lag here, so I may not see it right away, but go ahead and that times that, and then subtract it from 752, please. So the pressure of H2, that's what I need from you. In the meanwhile, while you're looking at that, I'll say, hey, we got 20 degrees C. We got the pressure. We got an R. And we got an answer. No, we don't yet. I'm still waiting for you to punch it in. I'm still working, so let's see if one of you can punch it in, and then I'll get it. Like I said, you may have already done so. I know there's a lag time till I get it. Good. And you guys got more or less the same answer. So 732.4 and 734.4. The values on the right are 732.34 kilopascals times 760 over 101.3. So 2.34 kilopascals times 760 divided by 101.3. And I got two rather different answers, so I need a third person to check this. Is it 732 or 734? No. Yeah. So 732 or 734. Can you guys punch it out again? And let's see. And Okay, so Isabella, you might be getting the number you got to subtract. So subtract that now from your, no, you're not off, but you got to subtract that from 752 to get the right answer, I believe. I'm still waiting because I need, can others pull out a calculator and do this, please, also? Because I can't do this very well. Okay, so you got 734, so let's go with that. Okay, so 734 point, I see 4 for two of you, so I'll go 734.4 millimeters of mercury. Thanks for doing that. Please, everybody else, pull a calculator out for other problems. Okay, how are we going to get the moles of H2? How are we going to get the moles of H2? We're going to use what nice thing? Hint, I got the pressure, I got R, I got the temperature. The moles of H2, what can I use? Beautiful. It's the word, it's the word. Okay, so here we go. We're going to solve for N. So we're going to go pressure. That's the pressure we worked so hard to get. 734.4 millimeters of mercury times the volume. There it is, 0.948 liters. Divided by R. And it's going to be the one that's in millimeters of mercury, which is not 8.31. Fiddly D, Miss Scarlett. Which one was it? I think it's like 60 something. There it is. Okay, so 62. Look at it. Look at Alicia's already got it, and so does Bella. Okay, 62.36. So 62.36. And it's got a liter torr mole Kelvin. So a liter, in our case, millimeters of mercury divided by mole Kelvin. Why do I do that? Because I just want to mentally make sure I'm using the right labels. So I put those in. Okay, divided by the temperature. Gang, 20 degrees, we got to change it to Kelvin. So help me do that. 20 degrees would be 293 Kelvin. Any of you quickies got it there? Some of you probably already punched it in. Huge. Okay, so let's get N. I'm going to put it down here. So N of H2. Let's not forget what we're getting. I know we're not at the penny yet. We'll get to the penny. Don't worry. Don't worry. This is the hard part. Okay, I need an answer. So could all of you punch it out? Thank you, Feeny. That's right, 293. Could everybody punch it out? Bang times bang divided by bang bang. So 734.4 times 0.948 divided by R, which is 62.36 times 293 Kelvin. Good, I got an answer. I'm going to write it. Let's check for a couple others, make sure I got the same thing. Yes, I got two that are virtually the same, so we're going to take those. So N is, I got 0.03. I got an 8 and I got a 9. We'll take the 8 this time. 0.038 moles and H2. Okay, gang. 62.36 is liter millimeter mercury per mole Kelvin. And Sophie, you got 9. Okay, two of you got 9. All right, we'll take 9. Okay, look back at your reaction. I erased it, but look back at your reaction. For every mole of H2, how many moles of Zn? What's the ratio? So use the stoichiometry. And Sophie, you can look back in the book for that if you can't see it. 1 to 1. Good. Everybody's seeing that. So what that means is that's also equal to the, all right, and the N, the moles of Zn, is equal to the same thing. So 0.0039 moles. Okay, now think of where we're going. I want the percent mass of copper in the penny. Hey, we got the moles of zinc. Why don't we change that and get the hint of zinc? Right? The hint of zinc. So times, well, at 1 mole of zinc, can you still see that at all? Yeah, you can. 1 mole of zinc is how many grams? And luckily, my periodic table up here is not very helpful, but I got another one that is more helpful on the back of my book. So it's 65.38. Let's call it 65.4 because I round to the tenths place. 65.4 grams. I'm going to double check. Yeah, 65.4, right? So can you guys get for me how many grams of zinc we got? So grams of Zn. Well, I'm getting sloppy here. Let's put it down where the problem is. Bad teacher. So grams Zn. So you guys give me an answer, would you? So please, all of you, punch out a calculator. And while you're doing that, I'm going to raise Pivner and get a spot to finish up our problem. Is it long? You betcha. Is it typical AP? You betcha. For an FRQ, anyway. But it's kind of cool because we can actually do it. All right, so 2.55. So we're going to get the mass percent of copper. Well, let's do a little subtracting, right? We want the grams of copper. So I got to take what? The penny, 2.586 minus 2.55 grams of Zn. That's the penny. Holy moly, Batman. It is really not a lot, is it? We can just about do that mentally. What? It's 586. So I'd have a 6 left over. And then what? 8 minus 5 would be 3. And then a placeholder. Let's see if one of you has beaten me to it. Beautiful. You got it. I think. Yeah. So that's grams of Cu. So to get the percent, it's what? 0.36 grams. Am I right? Is that the right answer? I hope so. Divided by the mass of the penny. What was that? 22.586 grams times 100 to get it into a percent. And is that right? Did you guys get the same grams of Cu? I just did it mentally. Answer key could just be wrong. Well, but the answer says 3.6, 1%. We did everything right, so I'm guessing the answer key is wrong. Okay? We step by step did everything I can think of, including using the balanced equation. So I'll look back at the problem, but I don't think there's anything that we've forgotten. The penny problem. No, that's pretty standard. So if the key has another thing, I think the key is wrong. Sometimes it is. Good. Questions on this problem? And if not, then we'll go on and take another one. But let's see before I erase this if there's anything you want to ask about. We got one from Bella. Okay, so And it's very much on the same page just about. So same page, just across to the next page, number 11B. That sounds good. All right, I'm going to erase and make a little board space. I hope this helps. I'll try and get this as close as I can. Here, maybe I can move this a tad closer. Then I lose some of it and you lose me. That's all right. You know what I look like anyway. All right. I'm trying to get close enough so you can see the tiny little whiteboard I got. So, page 489. We're doing 11B. So the same spot, really. And let's see what we got. So the top info, 239.4 milligram sample of a drug designed to treat malaria was run through a series of reactions to convert all the nitrogen into N2 gas. Okay. The gas collected over water, same thing, right? At 23.8 and a pressure of blah, blah, torr, at a volume of this millimeters of mercury. The vapor pressure of water at this temperature is, okay, at least they give us that. Okay, so B, a 3.239 milligram sample of the drug is combusted in air to produce 8.785 milligrams of CO2 and 1.60 milligrams of water vapor. Determine the percent biomass of copper and hydrogen in the sample. Assume that any remaining element is oxygen and calculate the empirical formula. Okay, this is an empirical formula problem, and we haven't done one of these in a while, so it's a good review. It's a good review. We've got to change. All right, let me just look and see if we've got to do anything with a wet for pressure. Okay, so we got milligrams of the drug, we got milligrams of CO2, so we don't have to fuss with a wet gas there, and we got milligrams of water. I think that's all okay. Yeah, so it's a percent mass problem. I may not even do the whole thing, but I'll do enough to get you far enough. Okay, so folks, what do we got to do? We got to change the grams of each of those, or milligrams to grams, and then change them both to what? And I'll start to do that while you're writing. What do I got to change my milligrams to? So 8.785 milligrams of C and 2.160 milligrams of H2O. All right. CO2. Yeah, okay, so Bella's telling us we got to change it to grams. Okay, so good. Mill is 100, so divided by 100, everybody. So wham, wham, wham. So it's 0. And you can do it with me. So 1, 2, 3. So 0.008785 grams of CO2. This one is 0.00. All right. 0.00216 grams of H2O. Does that look right so far? Check me and see. Bella's got the same thing I do up here, and hopefully the same as what I got down there. Okay, so we're going to have to change grams, everybody, to what? I can almost hear you yell it. You got to yell it a little harder, right? Got to change grams to moles, right? Okay, so let's do it. Here we go. So for every, okay, careful here. For every 1 mole of CO2, I get 1 mole of carbon. Do I have to do this? Well, only if you want to think about it. I know it's 1-to-1. 1 mole CO2 is 1 mole carbon. Oh shit. Okay. No, that's the second step. Pardon me. All right. Start again. Okay, so we're changing it to moles, and a lot of you said that. I'm glad. Okay, so now you can do it the right way instead of the wrong way. So we got to change to grams of CO2, moles of CO2. So 1 mole CO2 and is what? 12 plus 32 is 44 in my book. Is that right? And remember that for every 1 mole CO2, I get 1 mole C. Does that matter? No, except that I'm going to get here. I'm going to get the moles of C. Okay, and I got it from one person. I'll write it down. Can others check it? So 0.002160. 0.002160. That divided by 48. I thought it'd be like 0.000, but maybe that's right. I don't know. I think there's another 0 in there. Can somebody check that? Is it 0.00 or 0.0002? Because that would be dividing it by 4, and then divided by 44. Can you guys check that? So that number of grams divided by 44 grams. Point zero zero. So that's right. 0.002160. I'm losing my touch. Why does that seem wrong to me? So I divided by 10 would be another, and it's bigger than 10. Is that really right? Point 0.008785 divided by 44. So I get 2 times 10 negative fourth. Yeah, that's not right. Yeah, okay, good. All right, so you're with me. Okay, that's what I thought. Okay, I don't think that's right. So let's just round a little bit. 2.0 times 10 to the negative fourth moles of C. Okay? All right, let's do the same thing with H2O. And you'll see why I had to do this extra step here. You ready? So we got what? 0.002160 grams of water times grams per 1 mole of water. Better be what? 18, right? 0.0 times, okay, this is H2O, times, okay, here's the fishy part. Ready? It's 44. Yeah, it says 44, sorry. So that's the molar mass of CO2. Just do these calculations with me. So in case you can't read them, you know what's right, okay? Molar mass of CO2. So molar mass of water, 18. I hope you know that. But here's the deal. I got to do a ratio. 1 mole of H2O. It's got how many moles of H in it? You know what I'm saying? Here, CO2 is 1 to 1. But here, every H2O's got how many moles of H in it? Thank you, Chelsea and others. 2 is correct, so I got to double that. Good. Crunch it out, people. Tell me what you get. So that times 2 divided by 18. And I'll wait for a couple answers, and then we'll write it down. Times 10 to the negative third or fourth or something probably again. Oh, boy. All right. Okay. 2.4 times 10 negative fourth, and that's been gotten by a couple of you. Thank you, Alicia and Bella. So 2.4 times 10 to the negative fourth moles of H. Ahua. Okay. All right. So, holy. Okay. So, the problem has 2 questions in it. Let's look back on it. Determine the percent by mass of carbon and hydrogen in a sample, assuming that any remaining element is oxygen, and calculate the empirical formula. All right, folks, we got to get the first part's easy, okay? The first part, percent mass, I think you can do it now, right? Percent mass would be what? Let's just do percent mass of C, and then you can do O. So C, it was, pardon me, it was, oh man, that's CO2. Dag nabbit. This is taking forever, and I don't really want it to. Butter. Okay, all right. So for the percent mass of C, you need not the grams of CO2, you need the grams of C. So percent mass of C, it's going to be the mass of CO2, 0.00875, oh Lord, 85. What a stupid number. Grams of CO2 times, okay, how can I get the grams of C out of there? All right, I got to do a ratio. So for every 44 grams of CO2, that's the molar mass, right? How many grams of C are in that formula? Remember doing this a long time ago? Because we're trying to get the grams of carbon that are in the CO2. So to do that, I got to take this ratio. Total molar mass, but now I just need the molar mass of 1C, which would be what up on top? Hang with me. We're going to get this. Okay, I got at least, let's see there. So 12.0 grams of C. Okay, that's going to give me the grams of C I got. Okay, grams of C. Now, once I got the grams of C, I can do the percent mass. So percent mass equals the grams of C divided by the grams of the drug. So the grams of the drug in part B are 3.239 milligrams, but I got to change that again. 0.00. Is that right? 1, 2, 3. 3, 2, 3, 9 grams. Okay, what'd you get here? Exactly, good. Can you now do that division? So it's going to be, that's 12. Can you now do this and tell me what you get? So how many grams of C do I get here? Okay. Can you do this number times 12 over 44 and punch in what you get? I'll do the same because there seems to be quite a lag today. 0.00. No, that's not it. 0.008785 times. Okay. Yeah. Okay. Thanks, Ellie. I got the same thing. So 2.39 or 4, whatever, times 10 to the negative third. So I'll put it over here. 2.395, whatever. 6, let's say, times 10 to the negative third grams. Okay, divide that by that, and then please do by 100, and you get your percent mass of C. Okay? Oh man, that was a lot of work. Okay? Do the same thing to get the percent mass of O. And unfortunately, I got to do that because we got to get the grams of, do the same to get the percent mass of H. Okay? We got to get the grams of hydrogen. So we got to do the same darn thing here. So the percent mass of C, let's do that with H. Percent mass of H is, now we got to get the grams of water. Where was it in all this mess? It was 0.002160 grams of water. Okay, times. Okay, I need the grams of H out of there. Great, thank you, Isabella. Okay, so I need the grams of H out of there. So it's going to be what? For every 1 mole of H2O, I got how many grams of hydrogen to get the grams of it? Oh, Helen, I did it. I did it the wrong way. God darn it. Let's do it the same way we did up here. Let's do the molar mass of water. So we got 18.0 grams for the whole mole of water. And then we got in that 2.0 grams of H, right? H2O. So for 2 hydrogens, I need that. So essentially, we can just divide this thing by 9, if you would do that. And should be a comma. So you want to divide this by 9 here. I'll just do that too. Okay, you may be quicker than I. Yeah, you're all quicker. They're getting quicker. Okay, so 0.002160 divided by 9 equals. Okay, so I get 2.4 times 10 to the negative 4 grams of H. All right, percent mass of H then is that number, 2.4 times 10 to the negative 4th grams of H divided by the gram of the sample, which is again this sucker, 0.003239 grams of the drug times 100. And then you'll get your percent of H. And I got to do some erasing. So make sure, I'll send this to you in case you got to check the numbers, okay? But I've got to erase some up here. I don't have any choice. Okay, what'd you get for the percent mass of the H? You guys got 74% for this one. So it's certainly going to be less than that, right? Going to be 26% or less. Remember, we got some O in there too, so it's probably going to be less than 26%. Okay, let me know what you get here, a couple of you, when you get your percent of H. So you're taking the grams of it divided by the grams of the total tablet or whatever it is. Drug, grams of the drug. Y divided by 9, all I'm doing is saying 2 divided by 2 and 18 cancel out and make a 9 down here. You can go ahead and multiply by 2 and divide by 18. But I'm just reducing it. 2/18 is a ninth. That's all I'm saying. Good. And Ellie also got 74%. Okay, can you now punch out the percent H, everybody? Let me know what you get. Blank. Okay, 7.4% for the H. Okay, so I bet you can get the percent O too, right? So percent O would be 100% minus the other two, minus percent H plus percent C equals percent O. Okay, so where are we going with all this? That's to get the percent of by mass of carbon and hydrogen. Okay, well, okay, they didn't even ask for the percent O, but you got it anyway. Assume that any remaining element is oxygen. Calculate the empirical formula. Okay, so I got to erase all this. And I'm going to give you then just a plan to do the rest. Okay. We're getting really hunkered in the details. Okay, easiest way to get the empirical formula. You don't have to do it this way, but I'm going to tell you, it's the easiest way. Assume you got 100 grams. Assume 100.0 grams of the formula. So use your percent mass of the three elements C, H, and O to get the grams that would be that element out of the 100. So for example, if you got 7.4 for H, okay, so you're all ready. Use percent mass to get grams of each element. And then 3, change all to moles. Change each grams to moles. And finally 4, divide each answer by, we did this, but it's been a while, by the smallest mole number. To get ratios. And then 5. If they're not whole numbers, you got to multiply by 2 or 3 or something like that. Remember doing that? So it's in parentheses, multiplied by 2 or 3, blah, 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 if not whole numbers. And I'm going to let you guys finish up that. So let's talk about it. So, for example, for you and I, we had 7.4. Okay, we had let's take H. Everybody agreed on there. C, let's agree. So we had 74% of C. So for example, 74% of C, it's not going to be 74 grams of C, times 12 grams per 1 mole of C equals blah, 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 moles of C. Okay, you can do that with each of them. And then 3 or 4 here divide by the smallest mole answer you get of the 3 chemicals, C, H, and O. And then hopefully it'll be a nice ratio, and then you can put them in a nice ratio. C something, H something, O something. And those numbers you'll have from the moles down there, right? And again, if you got to multiply by 2 or 3 or something, do so to get whole numbers. We did that earlier in the course. Okay. Holy moly, Batman. That took a while. In fact, that took pretty much all the time I wanted to give this meeting. So we had from what? We had 9:45 to 10:45, and I've got a meeting at the high school. So I think we're going to do it this way. Tomorrow, Thursday, we'll do in class again. I'll take the first period. Maybe we'll just do an hour, and that way we don't have to have that stupid 20-minute break in the middle. So tomorrow, let's see if everybody's okay with this. We'll do 6 periods. So we'll do like 12:20 to 1:20, all right? And the first half hour, I'll take some questions, and then the second half hour, we'll start with the new book and do some more in chapter 1 of book 2. So I hope that sounds fair to you. And so then I'll see, I hope most of you tomorrow. I'll send this to the others that were not there. That sound okay? All right, then I will see you all tomorrow. And away we go. Luckily, you'll have the video. I'll send this to all of you right away via Google Classroom. Okay? So here we go. Adios, amigos.